recorded forever. Okay. So, recurring decimals. Do you know? Give me an example of a recurring decimal that you know already.
So 3.3 repeating.
Okay, I'm going to change that slightly to 0.3 recurring. 3, 3, 3, 3. Do you already know, and if you probably do, how to write that correctly? Yeah?
0.3.
Okay, so we've got a couple of options. 0.3 with a line, or 0.3 with a dot. Okay, and that notation means that the 3 recurs forever. Okay, so recurring decimals are when the number goes on forever. Alright? Now, does anyone recognise that one as a fraction already?
Yes. 1/3.
Okay, so we already know that that is 1 over 3. So that means that we ought to be able to go from a decimal to a fraction without too many problems. Not all decimals can be written as fractions, but what we call terminating decimals, like 0.25, that's it, can be written as a quarter, you know that. All recurring decimals can be written as a fraction, that's what we're going to do today. The only ones that can't be written as a fraction are called, does anyone know? If you get the name right, you can have a dragon.
What was the question?
What was the question?
What was the question?
Anyone know the name of a number that cannot be written as a fraction? So for instance, pi
decimal.
is an example of one of this type of number. E is the square root of any prime number is one of these numbers because it can't be written as a fraction. Anyone know?
0. 0.
So every number is called 0.
No.
I don't want an example, I want a name for the whole group.
E.
0 can be written as a fraction. 0 over anything is 0, so therefore it's a fraction.
Could it be sin or something?
No. There's a particular name that they have.
I forgot the name of it, but it's the ones that can only be divided by itself in 1.
No, they're prime numbers. They can all be written as fractions. Like, you know pi from your calculator when we're doing the circle stuff. Pi can't be written as a fraction. What do we know about pi?
It's unfinished.
Recurring numbers, but the numbers are changing each time.
So you mean non-recurring?
No, but like it goes on forever. But
Okay, the recurring thing means it happens again and again and again.
No.
So yeah, it goes on forever, like a recurring number, but we don't have any pattern. There's no recurrence. So they're non-recurring decimals, but they have a name. They are called irrational numbers. Right. I don't care if you know that name yet. As you get older, you will have to remember that name. But numbers that cannot be written as a fraction are called irrational numbers. The numbers that we are dealing with that can be written as a fraction are therefore called rational numbers. So we are looking at rational numbers. Okay. Rational numbers. So all rational numbers can be written as a fraction. And most of the numbers that you know are rational. So any number really can be written as a fraction apart from, say, the square root of prime numbers. Well, in fact, the square root of any number that's not a square number would be irrational, but pi is probably the most famous one that you'll know of. So any other number, any recurring decimal can be written as a fraction, and that's what we're looking at. But let's just go back to this notation. So 0.33333 has a line or a thing. But there are other numbers, for instance, without going into what the fraction is at the moment. So I can make up any recurring decimal. So I could do 0.147147 and so on. So the pattern is 147 recurs. All right. Any idea how you would write that one?
Is it 0.1%?
So we write 0.147 and then do what?
147. Like 3 points.
3 points. So a dot, a dot, a dot.
Yeah.
Okay. Close, but not quite.
Can we round it up?
No, we don't round. We definitely don't round.
Would you just put the line of the dot over the 7?
Nope. Because I'll tell you why. If I wrote 0.147 and put a dot, that would be this number. 0.14777 and so on. So only, so that might give you a clue. Rika,
Can you put it on 1 and 7?
but go on, I think you're right, but say it again for me.
Can you put it on over 1 and 7?
Yeah, a dot. So if we're going to use the dot, we put a dot over the 1 and a dot over the 7 to show the start and the end of the recurrence. Okay.
Can't you just write
If
a line
we
on
want
it?
to use the line is slightly different in that the line covers the whole lot. So that's where the notation starts getting a bit different. Okay. So I like the dots. I don't like trying to draw a line over everything. Okay. So it's quite good. So here again, if I've only got one number recurring, it doesn't have. It could be the line just over that one number. All right. So it's quite simple, that notation. Yeah.
If it were, if the number were to be 0.147 and then 4444 and just keep going, would you put the line over the first 4 in between the 1 and 7?
No, see, that 4 is not part of these 4s. This would be the only recurring bit. Okay,
So you
so
do 1474.
it'd be 1, 4, 7, 4, yeah, and then a dot or a line over the 4. Yeah. So you only put a notation over the recurring bit. Yeah.
What about if it was 0.147 and the 47 was there?
So 0.14747 like that.
Yeah.
Or what do you reckon?
47. Before and 7.
0.147 and then dot dot, or 147 and a line over the 4 and the 7. Being careful that the 1 is not included if you do it with the line way. Okay? Make sense? So it's quite simple. Recurring decimal. Now, what do you think is the reason for using the recurring decimal notation rather than rounding, for instance? You could say, let's round it, but why would we use this notation instead of rounding? Exactly. It's more accurate. You know exactly the number you're dealing with without having to write it all down. Okay? 0.33333, quite often people write 0.3 down because they've rounded it, and then they use that in their calculation and it gets less and less accurate. The other work on upper and lower bounds, you can see, you know, you don't have to change it much and you get a big change in your answer. Alright? Okay, so there's the notation. Any questions on that? Any more questions, examples you want to go through?
On calculator, you said to do this, it's E.
No, that's the times 10 thing.
Ah.
Okay. Now calculator, I tell you what, it's a good thing to think about. Quite often you'll see on a calculator this one. So if that is on a calculator screen, right, what would you write down as the correct, accurate answer?
0.16 repeating.
0.16 with a dot. Why is there a 7 there then? Why is that 7 there, Yifan?
Because others a lot of 6 as
So what has the calculator done, Yifan?
7
Yeah, but why? What's it done?
because it is bigger than 5.
So it has done a rounding, yeah? The calculator has rounded the number because it can only get so many figures on, and it wants you to know that, you know, the next one is bigger than a 5. So it puts a 7, but that does mean you have to interpret what a calculator says. Right. Anyway, let's have a look at converting to fractions. So obviously I said all of these numbers can be converted to fractions. So let's have a look at how. So what I'm going to ask is, do you remember, which you should do, how to convert a terminating decimal? So we've got a terminate. Do you remember how to write that as a fraction? Now you're going to go straight to a quarter, but I don't want you to go straight to a quarter. So for instance, I want you to be able to tell me what 0.3 is as well. So what would you do?
For 0.35?
Yeah.
It's 25 out of 100.
Good, perfect. 25 over 100. So that's the quickest, easiest way of putting a decimal is a fraction. Now obviously 25 over 100 can be simplified. So we divide by 25 and we get 1 over 4. But this step is what's important. So 0.3, Ollie?
Is 1/3.
No, it's not.
3/2.
We've just said 0.333 is 1/3. 0.3 is not 1/3.
Is it 3 over 10?
It is 3 over 10. Do you understand why, Ollie?
Yeah.
Why?
Because out of 10 is 3.
But why? Explain it in
I don't know
terms
how
of
to
the decimal.
I don't know how to explain it.
No. Let me know then, and then you need to understand. That's where your lack of understanding will come from in a test. George, explain.
The decimal place is 10.
Okay, this is the tenths column. We have 3 in it. 25 here.
Yeah.
The last column is the 100ths column. So we have 25 over 100. Okay, so you remember doing that now, yeah? So 0.016 as a fraction would be, Sophie? 16 over 1,000. Perfect. Well done. Okay. They can be simplified, but I'm not worried about it at the moment. Okay. Let's move on then to, well, let's show that this one that we know, 0.3 recurring, we know is 1 over 3. Let's see whether we can get there. Alright. Alright, so I'm going to explain it to you. Luckily, with the recording, you'll be able to listen to this again, Eagle, in your own time. Therefore, you can do it over and over again so you understand. So, obviously, well, what's the problem with the 0.3? If I've got 16 over 1,000, that's easy. What's the problem with the 0.3 doing it in that way? So if I tried to think, what is that number underneath? What would be the problem?
Because it goes on forever.
So it goes on forever. So I can't write the 6 is in the thousands column, so write it over. It does, because it goes on forever. So what do you put? Something over an infinity sign? Oh, no, that doesn't work. So this is what we do. Right? Now, here's the method. I'm going to write 0.33. I'm going to write them all out. Just a few, not all of them, obviously. Just to show you what's happening. Okay. I'm going to call that, what should I call it? I'm going to call it x. Right? Because that's the number. I want to know what x is as a fraction. What is it as a fraction? That's what I want to know. Right? That and that. Right? Got to convert it. What I'm going to do is this. I am going to multiply x by, well, in this case, I'm going to multiply it by 10. So I'm going to say, well, 10 lots of x equals 3.3333. Are you happy that I can do that?
Yes.
You understand that 10 times 0.33 is 3.33? Yeah.
Why?
What do you remember? What do you do when you multiply by 10? The same thing with standard form. All the numbers shift up one space, yeah? If I multiplied it by 100, I would shift all the numbers up.
Two spaces.
And that's why it's better that we think shifting numbers than shifting decimal place.
The second one should be 3.3333. You
What?
write 5.
No, because it's infinite threes.
Oh.
Doesn't matter.
The reason I did that is because what I want to do now is I want to subtract one from the other. So this is where maybe in your head it's not going, what? Well, I've got 10 x's here. I've got 10 of them. I've got one of them here. If I subtract the 1x from the 10 x's, how many x's do I end up with? 9 x's. So therefore, if I do a subtraction there, right, so I'm subtracting one from the other, I'm left with 9 x's, and here's the clever bit. What happens to this? What's 0.333 going on for infinity minus 3, this, I'm doing it the wrong way around, aren't I? I should have done it the other way. I'm doing that, take away that one. What's this, take away this, Nico?
0.
No. Anna? 3. Because do you notice, and this is the thing about the infinite number of 3's, I can subtract an infinite number of 3's from an infinite number of 3's and get left with nothing. So,
Isn't it minus
Yeah, that's why I
3?
said 0, because you're subtracting
no,
the
sorry,
decimal
I said
places.
the wrong way around. I'm doing 10x minus x. Yeah? So I'm doing 3.33 minus 0. I have written it, but in my step by step. So I'm subtracting that from that. Yeah? So 10x minus x equals 3.333 minus 0.333, doing it that way. So actually these 3.33's cancel out and we're left with only that 3. Yeah.
So, why do you subtract x?
I subtract because what does it get rid of?
Decimal points.
It gets rid of the decimal points. And suddenly my recurring nature of the number goes. So I'm left with 9 x's is exactly 3. So that's the clever part. How do I figure out what x is then now? So I've got an equation that you can solve. So 1x will be equal to
3.
Oh
No,
wait, isn't it
solve it.
6.
What do I do with this to solve?
3 divided by 9, which is
No, it's not. 3 over, now you'll
1 over,
notice
yeah, 1/3.
3 over 9 is a
1
fraction already, and it does simplify to
1/3.
1 over 3. So that's how I get the fraction.
Yeah, that's what I said, 1.
It's not 1, it's 1/3.
Yeah, exactly. No, I went on the top.
Mr. Fox, so you don't really need to do anything else.
Егор, ты рожден на
If
математике.
it's
Какой
0.6,
реальность ты родился и
it's
не
just 1
математик.
over 6.
No, it's not.
Я математик.
Let's have a look at that one. Couple more. I appreciate. It's a good question though. Let's have a look. There is a quick way. We're not quite there yet, and you haven't quite spotted it. So you think 0.333 is a 3 because it's all the 3's. But let's have a look now at 0.6 recurring. Can you have a go at applying the method to 0.6 recurring and tell me what you get? Have a go at it. I'll put me on pause. Okay, so set you this one. Hopefully what you did, I'll write it a bit differently so I'm not confusing you now. I'll do 10x, and this is the bit we have to consider, why 10x? Now 10x, because that still keeps all the decimals lined up and leaves me with the whole bit. Okay. If I do the subtraction, okay, right, you can see the subtraction, subtract that, leaves me with 9x equals 6. So we get, and this is the important bit actually for those of you that are going to spot the quick way, x is 6 over 9. The other one was 3 over 9. That bit is not so useful. That bit, however, is very useful. for a quick way. 6 over 9, which obviously simplifies to 2/3, which we should know. 0.3 if you double it, 0.6, double 1/3, 2/3. But 6 over 9 is very, very useful. Think 6 over 9, 3 over 9. Well, let's see what this one comes to. So x equals, now we figured out that if I write it over here, again, 0.147147. Someone did point out that if you do the 10x, you get 1.474. And what's the problem? Anna?
When you minus it, you still have a decimal.
Yeah. How many decimals?
A lot.
Infinite, still. If you subtract that from that, you don't cancel out the decimals. You get left with 4 take 1 is 3, 7 take 4 is 3, 4 take 7 is minus 3. It's a mess. It's an all-out mess. So 10x doesn't work. So we have to be a bit smarter. So what do we do, Ilya?
You do 1,000.
Times by 1,000. So we've got 1,000x, because what that does is it moves a whole block of these numbers up and then leaves the next block to line up. Okay? Then when you do the subtraction, you end up with 999x equals 147, which means x equals.
147 over 99.
What do you notice about the number and the nines?
How many zeros you divided it by?
You've got a really complicated way around.
I don't know, but the same amount of zeros and the same amount of nines. So if you have 10, it's just enough. It's just over 9. If 1,000, 3 zeros, so it's 9.
So what Jess is saying is whatever you need to multiply by, that's how many nines you need underneath. So the 0. What I would say, a bit easier for me to comprehend, was that however many digits are in the recurrence, that's how many nines you need to divide by. Yeah? So we can suddenly get to a much quicker solution, which is if I do 0.2934293429, for instance, so I've got 2934 recurring, we should be able to go straight now to a fraction is
10,000.
234 over 999.
perfect.
Wait, you can simplify the 147.
Well, yeah,
over the-
obviously.
Not that, I don't know about
Well,
that
the
one,
thing
but that one
is-
you can simplify.
The simplification is something you still have to do, but it's done as a fraction straight away. You know, if that's the task, write it as a fraction, it's done. The next phase is simplifying it. Yeah? And to be honest, when you've got this type of fraction with nines underneath, it's not always easy to simplify. So we would use our calculator to simplify it
Are we going to have a test on this?
eventually.
Or will we be able to use our calculator?
Right,